Hey guys, today let's just start off with a problem. As you can see, I have my collapse set up already, and we'll be discussing the vector reduction problem. What we need to do is, given an array or a vector, we need to reduce it to a single value using the addition operator. Or in other words, you need to find the sum of all the array's elements. So let's start by writing the serial code for that. So that declares my random array for the CPU. And the serial function would be something like this. Declare a variable to store the sum and iterate from 1 to size of the array, find sum, and then return the sum. And we can do that by its sum equals so we get sum. So that's that. Now for the parallel one, let's say we have parallel reduce which takes an a again, and I have my index equals thread idx of x plus block idx of x minus 1. Okay, I'll just skip this part. And then I check for bounds if idx less than or equal to size of a comma 1. Then let's add that up. And here I just store the sum into a of a of 1. So I'll be doing idx. And since 1 will already include that, I should make sure that it's not added again. So I'll just do if idx greater than 1 and idx less than size of 1. I'll compute that. Just return nothing. And so that should be the parallel function. So now let's get our device array, array of h underscore a, and let's call the function at CUDA blocks equals ceil of m by 1024, threads equals 1024, radius of d underscore a, and an error. Oh, sorry, it's parallel radius. And it runs. So let's copy this back to host. No, that's not nice. Equals array of d underscore a, and that test is approx head sum, right? Okay, it's sum comma h underscore a2 of 1, and that's wrong. As you can see, my actual sum is way more than the computed one. Why is that? Let's have a closer look at how this line works. Suppose I had a plus equal to b, or in other words, it was a equals a plus b. How would this actually be executed? There are multiple steps. First is the value of a is read into some register, and the value of b is read into some register. So there's first the read phase. After that, the values are computed and stored in some register. So then there's the compute phase. And once the computed value is in some register, it is stored back into the memory location of A. So that's the write phase. Now these three happen when I execute something. Now when we run parallelly, remember there's no guarantee on how the threads run or what will finish first or what will happen. So suppose consider this scenario. Thread 1 would read value and compute, and it's yet to write. And in the meantime, thread 2 reads that value, and it also computes the value. And after it computes the value, suppose say thread 1 writes the value, and then as usual thread 2 also writes the value. What happens here is that 2 read the value which was also read by 1, and whatever was written by 1 got overwritten by 2. So basically we're losing the value computed by 1. So we're just losing one of the array elements in the array. Hence you can see that it's always lesser than no matter how many times you run. Okay, if you noticed a change in these values and the cell numbers, that's because I just reran the entire thing once again. If you didn't, don't bother going back. Okay, so we're discussing this. So what value is lost and what value is stored depends on which reads what value and which value is overwritten and which value is lost. Or in other words, the final answer depends on the order of execution of the threads. This situation wherein the final outcome depends on the order of execution of the threads, which is unpredictable, is known as data race, and this needs to be avoided at all costs. The way we can avoid this is by using something called atomic operations. These operations make sure that when one memory location is being accessed by a thread, it does not allow the other threads to access the same memory location. That is, it stalls the other threads. So at a time, only one thread can access that memory location. So by just modifying this as at atomic, and let's run and check the test passes. Cool. Now let's benchmark it and check. I just ran the benchmark test for both of them, and as you can see, the serial is faster than the parallel one. Interesting. And there's a reason for that. By doing at atomic, what we're essentially doing is making this entire thing serial itself, right? Because there's nothing parallel about this if one thread is being stalled due to another. So you might say it should be the same time, but it's not, because apart from just adding, at atomic also forces one thread to check if that memory location is free or it's being accessed by some other thread. So those checks incur additional time, and this is slow. So back to square one. We need to come up with another idea. So far in serial, what is way we're doing is this thing. Add 0 to 1, then add it 2, add 3, add 4, add 5, and so on. And the parallel version we just wrote would basically do the same thing, but these numbers would be interchanged. That is, 7 could be added first, 5 could be added somewhere here, then 2 could be added here. It just didn't provide any guarantees on the order. Uh, Look at this diagram. This seems pretty much parallelizable, right? And in the end, we're summing up everything. First, we sum up 0, 1 separately, 2, 3 separately, and then we sum up those two added values. This is another way to sum up everything, and this can be parallelized because 0 and 1 can be added separately, 2 and 3 can be added separately, and I don't see any atomics required here because, yeah, they're not required. So let's try to write code which executes like this. Oh, and yeah, here we couldn't just have these many temporary variables, so we're adding it to the first position itself. And over here, let me just add it to the left element. That is, I'll sum 0, 1 and put it in 0. Sum 2, 3, put it in 2. And this is the 0 index diagram, but we'll be coding a 1 indexed one. So let's start that. First, the indexing. And then I'll have a variable called step, which tells first I have to add 0 with 1, then I have to add 0 with 2, then I have to add 0 with 4. You get the idea. So step equal to 1. And then we need to iterate throughout varying step values. And for that, the while condition be while step less than size of a command, because I don't want to make an out of bounds access. And while that's that, looking at here, thread 0 would add 0 plus 1. Thread 2 would add 2 plus 3. So thread 1 and 3 are doing nothing. So the condition would be something like if id mod step into 2 equal to 1. This makes sure that at each level we are performing the addition only for the left threads. Not left, but you get the idea. If that's that, then we do a of id plus equal to a of id plus stop. And an end, and here step into equals 2, because every time first I add 0 with 1, and add 0 with 2, and add 0 with 4, so it goes in multiples of 2. And don't forget to return. So let's run this and check now. Going back up, yeah, I'll reduce and test, and it passes. Let's check again, and it passes. Not good. Oh, okay, it was passing because I forgot to run the cell. So it was calling the other parallel function. Now let's check again. There was an error. Okay. Over here I forgot to check for out of bounds. And id plus strip less than size of equal 1. That should fix it. Unspecified launch failure. Okay, to I need to restart my runtime. Be right back. Okay, so as you can see, I have different values. I run everything, and my computed value is still less than the actual sum. So somewhere I'm still losing values. What could be wrong over here? I need you to think. It's related to the same problem that we faced earlier. Okay, I'll explain. Going back to this figure, suppose I was adding 0, 1, 2, 3, 4, 5, 6, 7. And I was storing this in zeros, so this in 2, this in 4, this in 6. What if 0, 1 was added? And before 2 and 3 was added, I added the new 0 and the old 2. I lost 3. This happens because no guarantees on order of execution of threads. So one might just go faster than the other. So I might lose 3 that way, or I might lose a bunch of values that way. So what we need is some sort of barrier over here, so that after all the threads execute this, they have to wait for the other threads to finish over here something to make them synchronized with each other. And that is done by sync threads. So synchronizing all the threads up to this point. Whichever finishes earlier has to wait for the last thread to finish, and then they continue. And make sure that you put sync threads in a region which is accessible by all threads. As in, don't put sync threads inside the if, because not all of them enter in. That's bad. Put it where each thread can reach that point. So let's try that now. And it's again test field. This time the reason is because of sync threads. Sync threads synchronizes threads inside a block only. So there is no inter-block synchronization, there's just intra-block synchronization. So the 1024 threads can be synchronized, but not more than that. So we'll need to modify our code again a bit to make it work. We can make it such that each block computes the sum of its elements, and then we can atomically add it to A of 1. That should work, right? Let's try that. So first we'll need to change this. Step can't go up to the length of the array, just can go up to block dimension of x. And then everything else gets to remain the same. This remains the same because my out of bounds check is still the same. And this works in coordination with the image based on how we're adding stuff. You can take some values and check it out. So let's, oh wait, I forgot to. Once this is done, now A of 1, A of 1025, A of 2049 will hold the respective sums of their blocks. After that, I need them to be added atomically to A of 1. A of 1 plus equal to A of ID, and the condition is if ID no, thread idx of dot x equal to 1 and ID not equal to 1. This is to ensure that it's the first thread in each block, and this is to ensure that it's not the first thread in the first block because that'll already be there. So, and then an end. This should work now. Let's check it. And it fails again. What did I miss? Okay, so I did a lot of debugging. I reset my runtime and I finally found it. I'll walk you through the process. I realized one mistake was it should be less than or equal to size. It's one indexed. My bad. And then I tried a lot of stuff. I saw that this value is always less than this, so I was still missing some values. So I had a doubt whether my thread mapping was correct and I was reaching all the elements. So to check that, I came up with this. After I add a value to where it should go, I made that value as 0 and did the same over here too. After it was added to a 1, I made it 0. And in the end, I checked if any of them were 0. I would print it out. But it still came. I mean, I didn't get any output, so my thread mapping was correct. And I realized that I had missed add in bounds. Add in bounds. On doing that, my test passes. I guess I still missed the proper usage of inbounds, and I'll make sure that I update a video about it. I'll make clear of its usage soon. Okay, so now you learned two things: synchronization by using sync threads and atomic operations. Also remember that all kinds of atomic operations are not supported. There are few mathematical expressions which are supported as atomic operations, and the entire list can be found in CUDA website. I'll put the link down in the description below. Oh yeah, I almost forgot. Let's check the benchmark now. The serial one will still be the same low net slot. Oh wait, I changed the size of the array. So I'll have to do that again too. And it's the waiting time. Okay, it increased because I increased the size by 10 times, and now you can see the parallel one is faster because stuff is actually happening in parallel as compared to this one. So that's it for this video. Make sure you do your assignments. Thank you.